I'm now going to talk about analogue voltmeters, because these were the first meters that I used in cathodic protection, and they were replaced much later by digital voltmeters, and this caused a complete re-evaluation of the so-called pipe to soil potentials. So it's important that corrosion engineers, especially those who've read Peabody's, the NACE publication, on versions before the 1970s and 1980s, because all of their theory and practices were based on analogue voltmeters. This is an analogue voltmeter. It works like this. Whoops, wrong card. Just a moment, sorry. Oh, cock up. Right, it works like this. This is the positive pole of the meter. This is the negative pole of the meter, and there must be current flowing through the meter, because that goes through a coil of wire, and this induces the movement of a magnet. I've put north and south on the magnet. This is connected to the pointer on the meter, and the magnet is held in position by a spring, a very, very thin spring, which can be adjusted at the top by turning a screw hole. Now, the importance of this is that the spring has a mechanical resistance which is based on the elastic memory of the metal of the spring. So the charges going into the meter induce a movement which forces the magnet to go against the pull of the spring, and how far it goes on the meter is the voltage that you are measuring. Important thing is, it must have a current, otherwise it won't work. The meter draws current from whatever you are measuring. Right, so let me show you the meter. Here is the meter. Here it's connected to, was connected to a battery, connected to a battery. And the charges go from the battery, the positive of the battery, into the meter. They go round a coil, and when I switch it on, whoops, you can see that the magnet has turned in that direction against the elastic memory of the coil, the spring coil, sorry, spring, not the coil. The coil is copper wire, the spring is steel of some sort, I believe. It's a hairspring, like you have on watches and things like that. Right, so as you can see, the meter has gone across to here. Here is 0. When it is at rest, you have to adjust the 0 with a screwdriver to make this needle fall on the 0 that is marked on the meter face, on the display face. Okay. Show you the drawing again. So this is the battery is across here. The charges go into here, round the copper coil, which induces a magnetic field which turns the pointer across the gradation marks, and that is how you get your reading. The important thing is that it takes current to drive the meter. So, where is that current coming from? Well, when we're measuring pipe to soil measurements on a pipeline, the ground is charged up by the transformer rectifier. The charges spread out to remote earth, and then they seek to return to the negative of the transformer rectifier. If there's a coating fault, they go into the coating fault and return that route. If there is a meter, an analog meter attached to the test post, which is connected to the pipe metal, the charges can then go into the meter through the half cell, or the copper-copper sulfate ground contact, and they go through the meter, which shows the reading on the meter, and then they return, the charges return through to the transformer rectifier. The effect of this is that the ground here has lost charges. So this is the same as having a coating fault here. Charges go from the transformer rectifier into the ground, through the analog meter to return to the TR. That is important for you to know, because I will later show you how this works in practice, because I will use an analog meter and I will measure the depression in the ground caused by the analog meter. I will measure this using a digital meter.